This is applications of the normal distribution. Now, to standardize a normal random variable, you're going to use this formula. Z is equal to x minus mu over sigma. Mu, again, is your population mean, and sigma is your population standard deviation. The random variable z is said to have the standard normal distribution with mu of 0 and sigma of 1 after you get done running through that formula. Now we got tables that we're going to use to look up some of this information. And about everything in this table is important. You see it gives you a picture here. And it indicates that we're dealing with the area to the left. And then your z-scores underneath. So keep that in mind when we're working these problems. It's the area to the left. And then our z-scores here, you see you've got negative 3.4, negative 3.3, negative 3.2, and so forth on the left side. Then across the top we have 0.00, 0.01, 0.02, 0.03, so forth. The hundreds place is across the top. The tenths place is here, and then of course the number before the digit is our integer portion. So like this first one here, this 0.0003, that corresponds to negative 3.40. Let me see, this one right here where my cursor is. That would be negative 3.0, and then the 0.04, so it would be negative 3.04. We'll see more of that. Let's look at our first problem here. It says, determine the area under the standard normal curve that lies to the left of negative 2.92. Here's negative 2.92. And it says, determine the area under the standard normal curve that lies to the left of it. The left of it would be this way. And it actually says standard normal curve, so it's already in terms of z-scores. So we got negative 2.9, that's our first digit portion, and we got 0.02. Those added together would give you this. So you kind of split it up. Take your hundreds place and put it separate. Well, negative 2.9, we locate that on the left side here. Here's negative 2.9. And our hundreds place is the 0.02. Well, here this column is the 0.02. So I look at the intersection of negative 2.9 and 0.02, and I see I got negative 0.0018. 0.0018. And that would be our answer. Now area corresponds to probability, corresponds to percentage, and so forth. So anyway, that's all they're asking on that. Now let's take a look at our second example here using tables. Determine the area under the standard normal curve that lies to the right of 0.53. So here's 0.53. To the right of is shaded this way. Unfortunately, our table is based upon the area to the left. Well, if I start out with everything. Here's 0.53. So there's everything shaded. If I subtract off from this the area to the left, it's kind of like I'm starting with this, I'm erasing this area to the left. Then that's going to leave me what I'm wanting up here, the area to the right. So this is 1 minus this right here. This is the tricky part, is you got to rewrite this in terms of the area to the left, because we can't work with area to the right. And when you think about it, all this area adds up to 100%. So we're just taking everything and subtracting off the left side, and that would give us the right side, which is what we want. Well, let's look this up in our table. Now this right here, if I were to split it up, I'd have 0.5, and then the hundreds place would be 0.03. So I come over here, I'm looking for 0.5 on the left side, which is right there, and our hundreds is 0.03, which is this column. So I'm looking up the intersection of the 0.5 and the 0.03. It looks like it's 0.7019. And if I subtract those, let's see, we got 1 minus 0.7019. And then we got 0.2981. And that's our answer. By the way, this is how it always works. If you're finding the area to the right, you always just rewrite it as 1 minus then the area to the left of that same value. So it isn't like every problem will be different. This is the way when you shade it to the right, that's how you always look it up with the table. Let's look at number 3. Determine the area under the standard normal curve that lies between 0.84 and 0.31. I should actually probably have those reversed. 3.1 and 8.4. And let me save that. So if I draw the picture, 0.31. Okay, that would be right there. And then 0.84 would be right there. And determine the area that lies between them. So we're shading this. We're trying to find this right here. Well, that's not based upon the area to the left. Well, let's envision that we start off with all this shaded. So everything to the left of the 0.84. I want to end up with this. So you look at that and you think, well, okay, what can I subtract off from that? That would give me the middle. Well, if I subtracted off this piece over here, to the left of 0.31. So if we subtract off this to the left of 0.31, that'll leave us the middle, which is what we want. And both of these are based upon the area to the left. So let's look up 0.84. So 0.8 and then 0.04 would 0.8 and then 0.04 is 0.7995. Again, the 0.84 we look up based upon the first decimal, well, this digit and then this first decimal place, and we look up the hundredths place, which is the 0.04. So I look up the intersection of 0.8 and 0.04, and we get 0.7995. Minus, now we're looking up the area to the left of 0.31. Again, 0.31 would be your 0.3. Let me put a plus here just to indicate that. Plus 0.01. So I'm looking up the intersection of 0.3 and 0.01. Here's 0.3, here's 0.01. So that would give me 0.6217. What did I say? 6217. Okay, so let's subtract these. .7995 minus 0.6217. And we get 0.1778. And that's our answer. Let me save this. Yes, applications. Try it again. Applications of normal distribution. Page 01.pdf. Okay. let's take a look at number 4 here. It says determine the area under the standard normal curve that lies to the left of negative 3.32, negative 3.32 left of, or to the right of 0.24. So here's 0.24, and to the right of that. Okay, well, I can split this up. This one's easy. The area to the left of that's already in a perfect form to look up in our table. Plus, and then we're trying to find this right here. Okay, so we said this is in the right form. So I'm going to leave it alone. Plus, and I'll put parentheses around here, we looked at this before. To find the area to the right, we do 1 minus the area to the left of that value. Because 1 is everything, that's everything shaded. And if I subtract off the area to the left of 0.24, that'll leave me the area to the right. So let's look this up. And again, negative 3.32 is negative 3.3 and the 0.02. Now I know it's not exactly added here because those two added don't give you this. But I'm just showing what we're going to look up. So over here, I'm going to look up the negative 3.3 and the column of 0.02. So negative 3.3 and 0.02 gives us 0.0005. Now let me double check that. Negative 3.302.005. Yep. Plus, then 1 minus, then the area to the left of that. So 0.24. Again, I'm going to look it up based upon 0.2 and 0.04. So this is our left column. This is our columns across the top. So 0.2, my left column here. This is 0.2, and then I'll look up in the 0.04, 0.04 column, and we get 0.5948. Let me double check that. 0.5948. Okay. Well, let's go ahead and plug that in the calculator. So 0.0005 plus, beginning parentheses, 1 minus 0.5948. Closing parentheses, enter. And we get 0.4057. And that would be our answer. Now with these examples, we're covering all of our cases, the area to the left, the area to the right, the area between two values, and then split it up like this. So, number 5. This says find a z-score such that the area under the standard normal curve to the left is 0.7. So they're telling us that the area to the left is 0.7, and they're wanting to know what this z-score is right here. So what I do is I take the look at the 0.7, and I look at my values in the middle here, and I'm looking for the one that's closest to 0.7. Well, 0.7 is 0.7 with 3 zeros. So I'm looking here for one closest to 0.7 thousand, basically. 0.7 thousand. Here, this one's 0.0015 off. This one's 0.0019 off. The one that's closest is this one right here, the 0.6985. So I come over to the left, and I get 0.5. And which one did we say? This one right here. So then I go up, and I get 0.02. Now, technically, we're not adding these together; we're merging them together. So this this symbol right here, we're merging them together. So this would be 0.52. So our answer is 0.52. Now, when I say we're not adding them together, because this could be a negative value, And again, we're just kind of merging two together. This is our hundreds place, and this is our tenths place. And then, of course, whatever digits here. Now that one was the area to the left, which is what our table's based upon, remember? So let's look at this next one. This says find a z-score such that the area under the standard normal curve to the right is 0.4. So what they're telling us, it doesn't matter how you do your picture, we're just trying to get a visual. They're telling us the area to the right is 0.4, and we're trying to find this value right here. Well, all of this adds up to 100%, so if this is 40%, this has to be 60%. So we're going to look it up in our table and try to find the value that's closest to 0.6, and then I'll add 3 zeros, so 6,000. So 0.6,000, and I come up here, 0.6,000. Here is 0.5987, that's 0.0013 off, and this one's 0.0026 off. So the 0.5987 is closest. So I come straight over to here, and I get 0.2. And I'm merging this together with the hundredths place. Which one did I say? This one here, 0.5987. I go up here, straight up, and that's our hundredths place. So 0.05. So our answer will be 0.25. Let me save that. Let's look at our next problem. Number 7. It says find the z-scores that separate the middle 90% of the distribution from the area and the tails of the standard normal distribution. So tell us the middle is 90%. Now this is symmetrical. So if 90% is in the middle, that means you got 10% in the tails. And specifically, since you have two tails, you'll have 5% in each tail. Now what we're trying to find is this right here. So we're trying to find this value. Well, if I look at this one, the area to the left of this value right here, where I'm drawing a line, the area to the left is 0.05. So if I come over here, I'm looking up 0.05, and then I put a couple zeros on there, so 0500. 0500. Down here I get 0.0505, that's fairly close. And here's negative 0.0495. Well, this one's 0.0005 off. This one's 0.0005 off. So these are actually the same in terms of closeness to this. So we're going to go halfway in between this. If I go straight over here, it's negative 1.6. Let's try it again. Okay. This one right here is negative 1.6, and I'm merging that. I'll put a little plus with a circle around it. And then if I went up to straight up to here, this would be 0.04, and this would be 0.05. So halfway in between will be 0.045. So this would, and again, we're not adding this, we're merging these together. Oops. Wrote that wrong. Let's try that again. 0.045. So again, it's halfway in between 0.04 and 0.05. So then this would give us negative 1.645. And that's our first value. So if you find one that's exactly halfway in between two of the hundredths place, then you take it exactly in the middle like that. Now this one, if I look at this one, here's the line, the red one. If I look at the area to the left is 0.95. So the area to the left is 0.95. And I want to write it in this form, so it's in 4 decimals. So obviously 0.9500 isn't in this table at all. So let's go to our next one here. Okay, we're looking in the middle here. We're looking for something close to 0.9500. Here's a 0.9505, and here's a 0.9495. Both of those are 0.0005 off. So if I go over here, I got 1.6, and we're merging that with, since it's halfway in between this one and this one, and this is 0.04 and this is 0.05, we're going to merge that with 0.045. So we get the number 1.645. Now you're going to find when we're talking about standard normal that if you got two values like this and it's symmetrical, once you get this one will be the same except for the sign will be changed. Okay, let's look at this one, number 8. And these revolve around switching over to our standardized z-score so we can look it up in the table. Then we'll look at how to do it on the calculator. Okay, so this is assuming that random variable x is normally distributed with a mean of 30 and standard deviation of 5. So mean of 30 and standard deviation of 5. Says compute the following probabilities. Be sure to draw a normal curve with the area corresponding to the probability shaded. So probability that x is greater than 42. So here's 42, and x is greater than means I'm finding that right there. Well, this is x equals. We want to change this to z-score. So first, we're going to use z is equal to x minus mu over sigma. Where am I getting that table at, or that formula at? Let me see. I'm on slide 12 here. So let me go back here. Remember this formula. Z is equal to x minus mu over sigma. So to get the corresponding z-score, we'll plug in the x, which is 42, minus mu, which is 30, over sigma, which is 5. So then 42 minus 30, what's that give us? 12? 12 over 5, which gives us 12 divided by 5, 2.4. Now you'd want to round this to 2 decimal places. So what our picture looks like now is z is equal to 2.4. And if you have it in terms of your z-scores, you can look it up in your table. But remember our table. Our table is based upon the area to the left. So I'm going to rewrite this as 1 minus, and then the z equals 2.4. And I don't think I actually put the tables on here, so I wonder if I can look that up. I'll bring up the ebook here. That's probably the easiest way to show it. Maybe. There it goes. Kind of slow times. Okay, where's my statistics book? Here it is. And this is back in the appendices. Which one is it? There it is. Okay. So we converted to z-scores, so 2.4. Now keep in mind what we're looking up is we got 2.4, 0. So we're looking up 2.4, and then in the hundreds place we're looking up 0.00. So 2.4, so here's 2.4 here, and then the hundreds place is 0.00, so we're looking up this value, so that's 0.9918. So this would be 1 minus 0.9918. And that gives us 1 minus 0.9918. And we get 0.0082. And that's our answer. So again, first thing we need to do is convert it to z-scores and then look up in our table. We're going to see the calculator is even easier, but first I want to show it using tables. So look at our next problem. These kind of encompass all over different cases again. And do I have room here? I probably do. So assume that random variable x normally distributed with a mean of 30 and standard deviation of 5. So mu is 30, sigma is 5. It says compute the following probabilities. Be sure to draw a normal curve with the area corresponding to probability shaded. Probability x is less than 25. So here's x equals 25, and less than is shaded this way, which is perfect for our table, but it's not in the z-score. So first thing we got to do is we've got to change it to a z-score. So we do z equals x minus mu over sigma. X is 25 minus mu, which is 30, over 5. 25 minus 30 is negative 5 over 5. So we get z is equal to negative 1. So our picture is we got z is equal to negative 1, and then we're shaded to the left. Now this is perfect for our tables. We got it in the z-score form, and it's the area to the left. Well, this is like negative 1.00, our z-score. So we're going to look up negative 1.0, again this digit in our tens place, and we're going to look up our hundreds place, which is 0. So we're going to look this up. Okay, so negative, turn to the next page, maybe not, turn to the previous page. Okay, there we go. So we're looking up negative 1.0, here's negative 1.0, and then the hundreds place is 0.00, which is this column. So negative 1.0 and the 0.00, I get 0.1587. And that's our answer. That's our probability. So let me save that. And let's look at our next problem. Okay. Probability, well, first the mean. Mean is 30, standard deviation is 5. And it says find the probability between 20 and 40. So here we have x is equal to 20. And here we got x is equal to 40. And we're finding probability, so that's same as area. Well, first thing, let's change these to z-scores. So we have to do both of them. So I'll do the 20 first. So we got z is equal to x minus mu over sigma. So plug in 20. So 20 minus mu, which is 30, over sigma, which is 5. 20 minus 30 is negative 10 over 5, which gives us negative 2. Now the 40. Again, we're plugging in the same formula. X minus mu over sigma. So we got 40 minus 30 over 5, which gives us 40 minus 30 is 10, and 10 over 5 gives us 2. So our picture has changed slightly. We got z is equal to negative 2, and we got z is equal to positive 2. And we're trying to find the area between it. Well, that's no good. because our table is based upon the area to the left. Well, imagine I start out with this picture here. Like that. And I got everything shaded to the left of the 2. I want to end up with this, so I think, okay, what can I subtract off from that? Oops. Shouldn't move my mouse when I'm doing that. Okay. What can I subtract off from this such that leave me the area in the middle? Well, if I subtract off the area to the left of -2, that'll leave me the area in the middle. And now both of these are to the left. So I'm going to look up this one. I'm going to look up 2. Now 2 is like 2.00, which if I split it up would be 2.0, and then the hundreds place would be 0.00. So let's look this up in our table. And come over to here. And here's 2.0, and then the hundreds place is a 0.00. So here's 2.0, hundreds place is right here. That would be 0.9772. Now this one here, this is -2.00. So I'm going to look up -2.0 and 0.00. Again, we're not thinking of like adding these, just splitting it up. This is our tens place, this is our hundreds place. So come over here. -2.0 would be right here, and then the hundreds place of 0 would be here. So that's 0.0228. Now there's a certain amount of symmetry here that I could have used to my benefit. I didn't want to worry about it though, but if I found the area to this, to the left of -2, that's the same as this right here, and the fact that these all add up to 1, I could use that to very easily come up with it. But again, I'm trying to keep it basic, always looking at the area to the left. So let's see what this gives us. 0.9772 minus 0.0228. And then enter. Here we get 0.9544. And that's our answer. Yeah, let's look at this one. Number 11. It says, assume the random variable x is normally distributed with a mean of 30. So we got 30. And standard deviation of 5. Find each indicated percentile. So the 15th percentile. Now, we're going back to this formula. Z is equal to x minus mu over sigma. Now, we're given the mu 30. We're given sigma, so those are given. What we're going to look up is we're going to find the z-score from the table, and then we're going to work backwards to find x. X is our goal. When I say find the 15th percentile, we're trying to find x. So let's go find the z-score. Now when I say 15th percentile, that means the area to the left is 0.15. That's what percentile means, the area to the left. So let's go look that up. 0.15. 0.15. Here's 0.1515. That's too far away. This one is 0.0008 off, and this is 0.0015 off. So the 0.1492 is the one that's closest to 0.15. So I'll go straight over to the left, and I get negative 1.0. Negative 1.0. And again, I'm merging that together. was this one, wasn't it? Okay, so that's, then I go straight up to here, and that gives me the hundredths place, which is 0.04. So our z-score is going to be negative 1.04. It's not exactly adding them, you're kind of merging them together. Okay, so now we know our z-score. So let's go to our formula. We got z is equal to x minus mu over sigma. Okay, so we'll plug in negative 1.04 for the z. X we don't know, minus mu, which is 30, over sigma, which is 5. Now we can multiply both sides by 5. And I think that's negative 5.2, but let me see. I'm not very good with decimals. So 5 times negative 1.04. Enter. Negative 5.2. Equals x minus 30. Take negative 30 over to the left side. We got positive 30 minus 5.2 equals x. And then 30 minus 5.2, enter. And we get 24.8. And that would be our answer. That's the 15th percentile. Let me save this. And start a new page. Okay. Well, there's got to be an easier way. And there is. We'll use calculator to do this. And you're going to find the calculator is so nice for solving these. That isn't necessarily difficult, but it's cumbersome. You know, trying to rewrite it in terms of area to the left all the time and looking things up in the table. Assuming I didn't make an error somewhere in there, which is probably pretty slim. Probability is pretty high. My eyes got off on one of those rows, one of those columns. So let's look how to do this. For the normal distribution for TI-384, if you're asked to find the probability, percentage, proportion, or area, those kind of all are the same item, you're going to use normal CDF, lower bound, comma, upper bound, comma, mean, comma, standard deviation. Now, if it's asked you to find the value, you're going to use Inv Norm, and then the probability will be the first thing you pass in, and that's always the area to the left. And then your mean, and then your standard deviation. And again, below I say, remember, area is equal to probability. Well, let's take a look at doing some of these on the calculator then. Okay, so number 12. Test scores are normally distributed with a mean of 65. So mean of 65 and a standard deviation of 5. So mu is 65 and sigma is 5. A, what is probably picking a test score out and getting one less than 70? Okay, so here's 70. Less than 70 would be shaded this way. Now, we treat this as negative infinity. So this would be negative infinity here. Now, we know if you're taking a test, you can't get below 0. So, you know, you could put 0 here if you want, but you're going to find there's not a whole lot of difference between putting negative infinity and 0 there. Well, how in the world do you put negative infinity on your calculator? Well, we use negative E99. And if you're wondering what that represents, negative E99 is negative 1 E99. There's an implied 1 there, which means negative 1 times 10 to the 99th power, which means you got negative 1 and you got 99 zeros. So you got 99 of these. That's a really small number. That's about as close as negative infinity as we can get. So put this in the calculator. Very easy. You do your normal CDF, and you do your lower bound. That's the for your shaded region. That's the value on the left. So that's negative E99, and then your upper bound, which is the one on the right, and then your mean, and then your standard deviation. So let's go put this in the calculator. It's under distribution, so You do second vars, and normal CDF is your second one, so you down arrow do it. Press enter. Then we'll do a negative. To get to E, do second comma. That puts your E on there. 99 comma 70 comma 65 comma 5. You can put a closing parenthesis if you want, and then enter. And we'll take it to 4 decimal places. So we got 0.8413. And that would be our probability. Let's look at B. What is probably picking a test score out and getting one more than 60? Well, here's 60. More than is shaded to the right. Well, if this is 60, then this is positive infinity in here, and we do positive infinity by E99. So I'm going to abbreviate this just as NCDF for normal CDF. And we'll put in 60 E99, our mean, which is still 65, and our standard deviation, which is still 5. So I do second vars, and down arrow normal CDF. And we said 60, comma, E, which is second, comma, 99, comma, 65, comma, 5, and then closing parentheses if you want, and enter. Those came up the same value, didn't they? That's weird. Huh. What are the odds that I'll make up a problem? They don't always come out the same, but what are the probability? I'll pick 2 numbers, and I just made these numbers up, and it comes out exactly the same. I know why. Because our mean is 65, and our standard deviation is 5. So if you add 5 to that, you get 70. If you subtract 5, you get 60. So it makes sense, but sometimes when you think you're being random and you're picking numbers out, well, you're not being as random as you think. They actually, one of the graduate courses I took, there's a procedure to test to see if somebody's making up numbers. You're not as random as you believe. C says, what is probably picking a test score out and getting one between 60 and 80? So here's 60, and here's 80. And between, we're shading here. So we'll do our normal CDF. You do your lower bound, which is 60, your upper bound, which is 80, your standard deviation, which is still 65, and or your mean, which is 65, and your standard deviation, which is 5. Sorry about that. So I'll do second vars, choose normal CDF, 60, comma, 80, comma, 65, comma, 5, enter. And to 4 decimal places would be 0.8400. So many 9s here that it rounds up. And that'd be our answer. Let's take a look at our next problem, number 13. And let me scratch my eye here. There we go. Let's see, ages. Ages of college students are normally distributed with a mean of 20 and a standard deviation of 5. So mu is 20 and sigma is 5. A, what is probably picking a student and getting one older than 25? So older than, what did I say, 25? So here's 25. And older than is shaded this way. So we're going to do normal CDF. Our lower bound, which is 25, our upper bound, which is E99. Clear to the right is E99. Comma our mean, comma our standard deviation. So let's put that in. So do second vars, normal CDF. 25, comma, now do second comma 99, comma 20, comma 5, and then enter. And we get 0.1587. 1587. Okay. We know a person can't be infinite years old. So instead of E99, let's say the oldest person in Cali is 100 years old. Maybe that's even excessive, but that would definitely cover all the cases. So if I do second vars, do normal CDF, and I'm going to plug in the same values, but instead of E99, let me put a reasonable value, like 100. I'm pretty sure there's nobody older than 100 here at Cali. And then I'll do 20, comma 5, enter. Look at what we came up with, 0.1586552596. They match all the way out that many decimal places. So even if it was off right here at the 5th or 6th decimal place, that's still not even enough to worry about. That's why we treat everything as infinity, just so we don't have to think who's the oldest person in the Cali and try to fill it out. Infinities are so much easier to think of in terms of these problems. Okay, B. Was probably picking a student and getting one younger than 16. So here's 16. Doesn't matter where you do your numbers, by the way. In actuality, your mean should be in the middle. But again, we're just trying to get a visual picture of this. So we'll do normal CDF. Our smallest value is clear over here, which is negative E99. Our largest value is 16. Our mean, which is 20, and our standard deviation, which is 5. So we'll do second vars, normal CDF. We'll do negative E99, comma 16, comma 20, comma 5. You don't need the closing parentheses at the very end in case you're wondering. And we get 0.2119. And that's our answer. Now C. Was probably picking a student to get one between 18 and 20. Move my mouse again. So between 18 and 20. So we'll do normal CDF, our lower bound, which is 18, our upper bound, which is 20 of our shaded region. Then our mean, which is 20, and our standard deviation, which is 5. So let's see, second vars, do normal CDF, 18, comma 20, comma 20, comma 5. Enter. 0.1554. Now your answer will actually be more accurate using technology, using calculator or Excel, than it would be using tables. Tables are bound by like 2 decimal places. If you're using z-scores, they're also bound by 4 digits. I'm rounding these to 4, but we could take them out more. Let's take a look at number 14. It says test scores are normally distributed with a mean of 65. And a standard deviation of 5. Now A says, what is the score that separates the top 10% of the class from the rest? So the top 10% of the class. So they're telling us this is the 10%. And if that's 10%, this has to be 90%. And we're trying to find this value right here. Now if you're asked to find a value, you're going to use Inv Norm. If it's not probability, it's not percentage, it's not proportion, it's not area, then it'll be value. And the Inv Norm is always based upon the area to the left. So if I look at the area to the left of this, it'd be 0.90. And then our mean, which is 65, and our standard deviation, which is 5. Inv Norm is under second vars. It's the third one. And we'll put in 0.90. Comma 65, comma 5, and enter. Now I'll take it to 2 decimal places. We get 71.41. That's the value that separates the top 10% of the class from the rest. Let's look at part B. What are the scores that separate the middle 95% of the class from the rest? Okay, so they're telling us the middle is 95%. Now all of it adds up to 100%, which means 5% is split up into tails. So this will be 0.025, and this will be 0.025. And we're trying to find two values here. So this particular value here, we're going to use Inv Norm on. And look where I'm drawing a line here. We're looking for the area to the left. Well, that'd be 0.025. Then our mean, which is 65, and then our standard deviation, which is still 5. Now this other value, we're also going to use Inv Norm on. Look where I'm drawing a line now, this red line. The area to the left of that, you have to add up all the area to the left. So you add up the 0.025 plus the 0.95, and that gives you 0.975. And then 65 and 5. So let's go type these in. So do second vars, Inv Norm. And first one is 0.025, comma, 65, comma, 5, enter. And we get 55.20. Taking 2 decimal places. And let's do the other one now. So we've got Inv Norm, so we'll do second vars, Inv Norm, 0.975, comma, 65, comma, 5. Enter. And we get 74.80, rounding 2 decimal places. So these would be the two values that separate the middle 95% from the rest. Now, you may have a problem, says if you get a certain percent that you discard, and if you get a certain percentage that you discard and ask you how many you need to start making to end up with 5,000 after the discards. For example, I'm working in a plant, and the contract is for we need 5,000. Well, if we know we're going to discard 5% of everything we make, scrap it because it doesn't work for whatever reason. Maybe the machine mills it a little bit incorrectly, so we can't use it. So we have to scrap that part. Well, if you want to end up with 5,000, this is how you find out how many do you start with. Now our formula is the total is equal to the start quantity minus start quantity times discard percent. And let's say discard percent is 5%, and we want 5,000. So put 5,000 in for total. I put S for the variable for start quantity, minus S times our discard percent, which is 5%. Now this is combining together like terms. There's an invisible 1 in front of this S, so you got 1 minus 0.05, which is 0.95S. And then you divide both sides by 0.95, and you get 5,264. And I think I rounded on that. So this gives you an idea of how many do you need to start with, given that your scrap rate is 5%, in order to end up with 5,000. So you can use this to help figure out some of your normal probabilities. Like if you just calculate your probability you're going to scrap a part is this, then you can use this to help figure it out. And that's actually the end of that. So let me stop the 2 recorders.